Okay, welcome back. So we have our exam tomorrow. So we're going to finish up chapter 10. We just have just a little bit more to go, just one definition left and an example. And then we can move on to chapter 10. Okay, so last time we were looking at the tangential and normal components of acceleration, right? And we looked to see how we can decompose these things, all of the factors in front of our unit tangent and all of the factors out in front of our normal tangent. So we were able to kind of break up acceleration and decompose it in terms of, where we're pointed, where we're going, and what's normal to that in this T and B frame. Okay, so another thing that we might want to calculate is called torsion. And torsion is how much the binormal vector changes with arc length. So the question is, how does the binormal vector change with respect to arc length? And we're going to try to relate this to our T and B frame. Okay. Well, the first thing that we can do is we can note that dB ds is equal to, by definition, the binormal vector. So we're taking the derivative of the cross product between t and n. So remember, that's how we defined our binormal vector. So we're just taking the derivative with respect to arc length of this t crossed n. So this is dt ds crossed with n plus t crossed with dn ds, right? And that was just going back to our differentiation of the product rule that we talked about earlier. So now let's kind of look at these terms and kind of figure out what's going on. What we're going to notice that dt ds is in the direction I should actually say the same direction. So if we go the same direction as our n. Right? And to do that, just kind of think about how you decompose this derivative with respect to, so if we wanted to say, how did we relate this to dt? Well, this is ds dt. Oh, no. That's not right. So dt ds is, so we need dt dt. There we go. Right? So this quantity here is just some scalar function, right? And you could think of it as the reciprocal of ds dt, or how time changes with arc length, whichever is better, but it is just some scalar function, right? And this is the direction that it's pointed in. Well, we know that this is pointed in the n direction, right? It's not normalized, it's not quite n, but it's still pointed in the n direction. So that means that this is also pointing in the n direction. And we're taking the cross product of two things that are pointed in the same direction, right? So that means that this term ends up being 0. So let's scroll down just a little bit. And that leads us to say that the derivative of the unit tangent vector with respect to arc length crossed with n is equal to the 0 vector. Thus, we remove that term, and it looks like the only thing that we need to be worried about so far is this t crossed with dn ds. Okay, from this, we can also make some observations here. So this means that dB ds is orthogonal to t, right? The cross product just generates a orthogonal vector to both of the things that use in the cross product. So we definitely know that it's orthogonal to t. Okay, so notice that since the binormal vector is of constant length, that dB ds is also orthogonal to b, right? That's that constant length derivative coming back in here. So this means dB ds is a scalar multiple of n. So then we say that dB ds is equal to negative tau n, where tau is just this scalar multiple that we put in front. The negative is just a choice. It's just something that physicists kind of threw in there. So most of the time that torsion, well, this tau is positive, and spoiler, the tau is our torsion. So we can actually say that torsion is negative dB ds dotted with n. So this might be pretty complicated to actually calculate. We don't want to find the binormal vector and then see how it changes with respect to arc length, right? That seems like a lot of work. Well, it turns out that this actually has a pretty nice alternative definition, or actually just kind of way of writing it. What we'll do is we'll express this as a determinant, where on the first row, and I'll explain what these dots are in a second if you don't know what they are currently. So we have a 3x3 determinant, and then we divide by the velocity crossed with acceleration and magnitude squared. And this is valid so that we don't have our denominator is equal to 0. So what do these dots mean? These dots are typically how physicists write time derivatives. So our position might be written like this, where we have an x, y, and z component as functions of time, right? And then here in this first row, we merely have velocity, here's acceleration, and then here's jerk, right? So our first, second, and third derivative of position. And we just take the determinant of this guy, and then we divide by the magnitude of the velocity crossed with acceleration, and then we square that. Okay, so let's do an example. Let's calculate it. So I'll write the prompt here while people can scribble that down. So our example is find the torsion of the helix. Helix is making a return. Ooh. Actually, that term in front of the sign should be an A. There we go. Okay, so in order to find the torsion here, I'm going to need the first, second, and third derivative. So I'll go ahead and calculate those. So r prime is this negative a sine of t, a cosine of t, b. We have our double prime, which is negative a cosine of t, negative a sine of t, 0, and then our triple prime is a sine of t, negative a cosine of t, and 0. Okay, so let's go ahead and calculate this determinant. Actually, let's go ahead and do the denominator first. So let's look at r prime of t crossed with r double prime of t. So that's velocity crossed with acceleration. So this is our I with negative a sine of t, negative a cosine of t, j hat, a cosine of t, negative a sine of t, and then k hat, which is our b times our 0. So in the x component, we're taking the determinant of this lower right block here. So we have a cosine of t times 0. It's nice enough. And then multiplied by b and a, or negative a sine of t. And remember, we're subtracting this. So we end up with a b sine of t. And then in the y component, we have the determinant of these two columns over here. So we have negative a sine of t multiplied by 0 minus b times negative a cosine of t. But remember, we also have the negative from the j hat component. So we end up with negative ab. Why are we doing r prime and r double prime again? We're calculating the denominator here. So we have ab cosine t. And then finally, for the z component, we're looking at the cross, or not the cross, but the determinant of this block here. So I have an a squared sine squared t plus this a squared cosine squared of t. So luckily, this term simplifies because we have the same coefficient out in front of the sine squared and cosine squared. So we can write this as ab sine of t negative ab cosine of t, and then just an a squared. Okay, so we need to find this in magnitude. So the magnitude of r prime crossed with r double prime is the square root. We have to square this term here, a squared b squared sine squared of t plus an a squared b squared cosine squared of t, and then an a to the fourth. So again, we have the same coefficient out in front of the sine squared and cosine squared. So we can, this term just here is just a squared b squared. And we can simplify that as a square root of a squared plus b squared. Okay, so now for the numerator, we have to look at the determinant where we have negative a sine of t, a cosine t, b, negative a cosine t, negative a sine t, 0, and then a sine t, negative a cosine t, and 0. Oop. Okay, so let's give ourselves some room here. We have the coefficient out in front of here, this a sine of t times the determinant of our lower block down here, but this is 0 times negative a sine of t minus 0 times negative a cosine t. So this is 0 minus 0. Nice enough. Then remember, we're subtracting the next element here. So we have a cosine of t multiplied by the determinant of these two columns. But guess what? We've got another 0 pair here. So this is 0 times our first element and then a 0 times our second element. So we get a 0 minus 0 here. And then our last thing is plus b times the determinant. Or maybe we should do this on another line just to give us sort of some more room here. So plus b times the determinant of our lower left block here. So here we get an a squared cosine squared of t. And then here we get minus negative a sine of t times a sine of t. So we get plus a squared sine squared of t. So our determinant here looks like it's just a squared times b. So that means that our torsion is this upper determinant, which we found to be an a squared times b, and then the magnitude of velocity and acceleration was our a square root of a squared plus b squared, but we had to square that in our denominator. So these a squareds will cancel here. So I left with a b in the numerator, and then all I'm doing is just squaring the square root. So I have an a squared plus b squared. And there's our torsion. And it's cool because it's a constant for the helix, right? It could have been for another generic curve that this is a function of time, depends where you are. But in this case, for the helix, the torsion is always the same, right? It's always moving the same, right? So you kind of expect that the change in this binormal vector with respect to arc length should be the same, because you kind of just have this simple spiral just moving upward. Okay. And with that, we have concluded chapter 10. So we have about maybe 10 or so minutes, just over 10 minutes. We could start the next section, 11.1, but that doesn't seem like too much time. We don't have really anything else. We could talk about the exam, but I don't know how useful that would be. If you guys have any questions about maybe the exam before we take our 5-minute break for the TAs, I guess you could send that into the chat box and I can try to answer them. Because with about 10 minutes, I don't want to try to cover this material and then have us have like a 3-day break from it. Okay, so I'm getting a lot of questions now, so maybe we do this. Okay, so first question that I have is the format all word problems like the fall spring exams. I have no response to that. It could be all word problems. It could be, you know, just, I want you to calculate this thing. Yeah, so, but potentially all of the exams in the past have had word problems in them. So you should definitely expect there to be word problems. But if they're all word problems, who knows? Well, I know, but you'll find out tomorrow. Will we be able to print the exam if we want a paper copy? You could print the exam. The problem with that is I can't give anyone extra time to print the exam. So as soon as you receive the exam, the timer starts. So that would be cutting into your time a little bit to print it. You're more than welcome to print it if that is more comfortable. But I can't give, like, say, the people that want to print it a 5-minute extra start or anything like that. It has to be at the same time that everyone gains access to the exam. Are we allowed to use earplugs or earbuds for the exam? Okay, so the TAs asked me this question. Yes, you can use earbuds or earplugs. You're going to be muted on Zoom. So if you want to just use your speaker for the music, or you want to use earplugs, that's fine. This is all right. So this is a homework question. Well, let's not do homework questions here. Let's talk about the exam. You can either ask the TAs in their recitation or in office hours after their recitation today. Okay, so are the previous exams, especially past summer exams, a good way to study? Yeah, I would definitely use the exam archive. Those are great sources for you. I have written some of those exams, so I kind of expect it to be of those caliber. You could potentially, go through the questions without timing yourself, kind of leisurely, to see like where your strong or weak points are, and then you could do a test run where you time yourself through one of those exams. It should be about the same length. So the difference between summer exams and main semester exams, I don't think there's much. It's still the same material, more or less. I think if you go back far enough that the material changes a bit. But I think the most recent exams, they're all chapter 10. But if there's something that just seems out of left field, then it's probably from chapter 11. Could you give an example of an application of torsion? What's a good example of torsion? If you're doing a lot of revolution or like angular calculations, we'll talk later about, I guess we're not really going to bring up torsion again, but we will talk about how to calculate like moments of inertia, and like when you're revolving objects around centers of mass and stuff like that. So anytime you have a concept in physics that is more or less, I don't want to say linear, but you think of force as this directional like concept. Well, you have torque, which is this kind of angular version of force, right? And then you have this like this concept of mass, right? But then you also have this moment of inertia, right? So we're always going to talk about one thing and then talk briefly about its kind of like angular version. And torsion is similar to that. Sometimes curvature and torsion are very closely related, and you can talk about them together. They're just like a different way of measuring how curvy the the object is. Just different measures. Like the different measure of if you walked outside, what is the total distance you've traveled versus your displacement, right? Just a different measure of kind of calculating these things. Any other questions? I ran out of questions here. No, we got about 40 people in this Zoom room. No questions about the exam yet. Okay, well then I will ramble about exam stuff, I suppose. Oh no, we're getting questions now. How long will we have to submit afterwards? So when the time is called, you will have roughly 20 minutes to upload your exam. So please try to, if you use your phone to upload your exam, or maybe you have a scanner or something like that, please, if you can have your camera still set on you while you're doing your upload or what have you, that would be great. So also kind of on the same key or the same topic of exams. So tomorrow, please show up a little bit early. We're going to have to try to check everyone's identification. So if you can bring your Buff 1 card or a driver's license, that's okay too. And then we will try to get everyone logged in. You'll show your cheat sheet at that time as well. So the process that I kind of outlined in that email that I sent earlier in this week, I believe. So you will be muted throughout the exam. If you have any questions, you will send them like how we've been doing the lectures via chat. You'll send it to one of the proctors. I will be there and our TAs will also be there. So you can send it to one of the three of us. And we will try to get back to you as quickly as possible. When you are completed with your exam, you will notify one of the proctors. They will give you the go-ahead to start the upload process. When you are done uploading, please double check that what you've uploaded is legible. Okay, you do not want to upload that's your exam and then come back maybe 2 hours later and then see that we just can't read it, right? I can't let you submit the exam again. So double check this to make sure that the exam is legible, right? Then don't leave once you've checked. Notify one of the proctors that you have completed the upload process, and then they will give you the go-ahead to go about your day. You'll log out after that. I think what is allowed on the cheat sheet? Anything that you want to write down on the cheat sheet. If you want to write down formulas, if you want to write down like properties for cross products or derivatives, or you want to write down example problems, you can write down whatever you want on your cheat sheet, right? The cheat sheet, in all honesty, is in making this cheat sheet, I think you are inherently studying the material that you put onto it. Sometimes it's a good reference if you kind of, you kind of panic a little bit during exams. It's great to have this kind of reference. But right, so this is tailored for how you learn. So put whatever you need on that cheat sheet. The upload process will be on Gradescope. Right. So you will be uploading your exams to midterm 1 on Gradescope, and that will open up tomorrow and then close right after the the upload window after the exam. Is it okay if you type your cheat sheet? I'm okay with that. I know people really like to cram a lot of stuff into their cheat sheet. So it's like it's written for ants. That's fine. I think that just gets you to study however you feel like you need to study. Okay, we have Teddy in the room. Teddy, do you want to chime in with any exam tips or anything like that? No, maybe he stepped away.
Dylan.